Okay, so let's start. Uh, Good evening, everyone. Uh, am I audible, right?
Yes, sir.
Yes. So, good evening, everyone. I welcome you all to this live session. First, let's introduce me myself. I am Suman Sadhu. I am a PMRF Fellow of Department of Materials Engineering of ISC Bangalore. In this live session, we will mostly solve the previous year grade question paper. And I mostly cover the topics from the crystallography, phase transformation, thermodynamics, and the characterization techniques. So the basically the idea is to make this session as much as interactive. So I request you all, don't hesitate to ask any question. So you can interrupt in between also, and also you can ask question after solving the questions also. So any kind of doubt you can ask during these sessions. So let's start solving this first question. So this is the question number 12 of GATE 2016 MT. Uh, the question is the lattice parameter of face centered cubic iron is 0.3571 nanometer, and the radius of the octahedral void in gamma iron is, so you have to determine the radius of the octahedral void in the gamma iron. So let us see the crystal structure of a FCC unit cell. So the screen is visible, right?
Yes, sir.
Okay. So this is the structure of a FCC unit cell. So it has 8 atom at the corner and 6 atom at the face center positions. So in this unit cell, the octahedral voids are located at the edge center and at the body center of this unit cell. So basically octahedral voids, it has coordination number of 6. So there is a 4 atom in this plane and 2 atom on the 1 atom on the top and another atom is on the bottom. So first let us consider this octahedral void which is present at the body center location. Now if we see this plane, so this distance is nothing but is equal to the lattice parameter A. So basically if we draw the octahedral void here, so that is that 4 atom is in the plane, one atom is at the top and another atom is at the bottom, and this is the location of this octahedral voids. Now let us consider this plane. So this distance is basically the distance between these two face center atom. This distance is A. Now if the radius of a iron atom is R, capital R, and if the radius of the octahedral void is smaller, then we can write that this is the one iron atom. So this is distance is R, then the octahedral void is there, so this will be 2R, 2 into smaller, and then again there will be another iron atom whose radius is R. So this total distance we can write that capital R plus 2 into smaller plus capital R. This distance is equal to lattice parameter of this unit cell. So now we can write 2 into capital R plus small r is equal to A, or capital R plus small r is equal to A by 2, or so small r is equal to A by 2 minus capital R. Now in order to estimate the octahedral void size, we need the relationship between this capital R, that is the radius of one iron atom, and the lattice parameter of this FCC unit cell. So anyone has any idea how can we calculate this relationship? So till now you have understood, right?
Yes, sir.
Okay. So next, in order to find out the relationship between this lattice parameter and the radius of the iron atom, we need to see the close back direction in the FCC unit cell. So what is the close back direction in the FCC unit cell? You can unmute and answer, and you can also type in the chat box. Anyone? Okay, so the close back direction in FCC is basically this 110 direction. So now if you see this plane which I am highlighting right now, this plane, that is a 100 plane. So this direction is 110. So in this direction the atoms are located in this way. So 4 atom is there at the corner, 4 iron atom is there in the corner, one and one at the face center position. So if you see this distance, so this distance is nothing but the summation of this distance, that is capital R, plus this distance, that is 2r, and this distance, that is r. So this distance is, total distance is r plus 2r plus capital R, which is equal to root 2 a, because this one side is, the length of this one side is equal to the lattice parameter a. So this distance is, the total distance is root 2 a. So now we have the relationship between this capital R and the lattice parameter of the unit cell. So 4r is equal to root 2 a, or we can write r is equal to root 2 a by 4. Now we can substitute this value to this equation. So we will get the size of the octahedral void r is equal to a by 2 minus capital R means root 2 a by 4. Now if we take a by 2 common, so this is 1 minus 1 by root 2. Now the lattice parameter for the FCC iron is given, it is 0.3571 nanometer. Now if we put the lattice parameter value here, we will get the size of the octahedral void. So lattice parameter value is 0.3571 nanometer divided by 2 to 1 minus 1 by root 2 in nanometer. I hope every one of you have calculator with you right now, right? Can you all just calculate it and tell me the answer? Hello? Are you people there?
Yes, sir.
Yes. Can you all calculate and tell me the answer? Yes, right. So the answer is 0.052 nanometer. So this is the size of the octahedral void which is present in the FCC unit cell in the body center position. So anyone has any doubt on this question, or if you have any general doubt also, you people can ask.
finding the location of the octahedral void, we have
Yes.
to visualize the crystal structure so
Ye-
that where position, like in what positions the void can occur. That way we need to do it.
Yes, yes. Like octahedral void, you know, right? It has a coordination number of 6, so it is basically surrounded by 6 atoms, right? So, one means 4 atom is located at the plane, and 2 atom means 1 atom at the top and another atom at the bottom. So, this is the shape of the octahedral void. Okay. So now, if we go back and see this crystal structure, so as you can see that one atom is at the top, another is at and means this 4 atom is at the face center positions. These 4 iron atom and one iron atom is the top, another iron atom is the bottom. So this is creating the one octahedral void at the location of body center positions. Similarly, you can visualize the octahedral void in the edge center location also. Right? If we consider another unit cell beside this unit cell, so here also this iron atom will be located at the corners and at the face center, right? So now again, if you consider this 4 atom and this 2, this one and this one, again another one atom will be there from some other unit cell. So this 4 atom, this 4 atom and one atom at the top and another face center atom at the bottom. So this will also create octahedral void at the edge center location. So this diagram may look a bit dirty, so you can visualize this way, like there are plenty of unit cell which are located at the surrounding of other unit cell, right? So that combination of the distribution of those atoms can create the octahedral void at the location of the edge center and at the body center also. So in this way you can visualize it.
Yes, sir. Thank you, sir.
Okay. Anyone else have any doubt?
No, sir.
Yes.
No, sir.
Okay. Okay. Then let's move to the next question. So is question number 13 is feasible?
No, sir.
Okay. Okay, I think that network is a bit slow, that's why it is happening. Now,
Yes, sir. Now
Yes,
it's-
sir.
okay, but what is happening? Now it is feasible, right? Yes.
Yes, sir.
Okay, so this is the question number 13. So for an ideal hexagonal closed pack structure, the C by A ratio and the packing efficiency respectively are option A 1.633 and 52%, option B 1.633 and 74%, option C 1.733 and 68%, and option D 1.733 and 74%. So in this we have to calculate the C by A ratio and the packing efficiency. So now let us see how the hexagonal closed pack structure look like. So it has basically AB type of stacking. So there is a different layer of stacking of atom. So this 6 atom is there at the bottom plane. So and this triangular kind of atomic plane, if it is B, so as you can see that, so this is a A type is stacking, sorry, one atom will be in the in between of this. So this is A type stacking and this is B type stacking, and again this is A type. So hexagonal unit set basically forms by AB type of stacking. So now we need to determine the C by A ratio. So this height is of the unit cell is C, and this is the lattice parameter. So now if we project this atom to this plane, it will intersect this plane somewhere here. So now let us magnify this area. So you can see that this top atom, if we are projecting it to this plane, it is intersecting somewhere here. So, and this is a stacking of this A type of B type of atomic plane. So let's name this triangle A, B, C. This is D, it is O and E. Okay. So this length is basically lattice parameter, that is A. So why this distance is A? Can anyone tell? Anyone? Okay, so for the sake of simplicity, this structure is drawn in like that these atoms are far apart, right? But in reality, so these atoms are actually touching each other like this. So basically this length, where this two atoms are touching each other, that is this length is A, the lattice parameter, right? So this length is A, or we can write it is equal to 2r, that is the radius of each atom. Similarly, if we see the B stacking, means this is stacking, here also these three atoms are basically touching each other. Those atoms are not far apart, so for the sake of simplicity it is drawn like this, but those atoms are basically touching each other. So this length is also 2r, or it is equal to the lattice parameter A, right? So similarly, these two atoms also are touching each other, because this A and B and A type of stacking are placed on top of each other. That's why these two atoms are also touching each other. So this length is also equal to the lattice parameter, or 2r, right? So this triangle ABC, that is this triangle, it has it is a equilateral triangle. So all the sides are having the equal length, which is equal to the lattice parameter. So from this triangle we can write that AB is equal to BC is equal to AC, which is equal to the lattice parameter. Now what will be this length, that is AD? So we know that for a equilateral triangle this length is √3 by 2a, right? Now this AO is basically 2/3 of AD. So 2/3 of AD means 2/3 into √3 by 2a. So AO is √3 by 3. So it is √3a by 3. Sorry. So it is √a by √3. So AO is a by √3. Now let us consider this triangle, that is triangle AO and E. So if we consider this triangle AOE, here we have AE, we know that it is equal to A. We also know AO, this is equal to A by √3, right? So now we need to find out the C by A ratio, right? So what is this distance? OE. OE is nothing but the half of the total height of this unit cell, that is C by 2. So OE is C by 2. Now from the Pythagoras theorem we can write AE square is equal to AO square plus OE square, which implies that AE square means A square is equal to AO square means A square by 3 plus OE square means this one, so C square by 4, or we can write C square by 4 is equal to 2/3 of A square, which implies that C square by A square is equal to 8 by 3, or C by A is equal to root over of 8 by 3. So if you have calculator, you can check that this root over of 8 by 3 is equal to 1.633, right? So you have the C by A ratio is 1.633. This is remember, this is for the ideal hexagonal crystal structure, but in reality some of the crystal structure are distorted or something like this. So in that case the C by A ratio may not be equal to the ideal C by A ratio. It may be a bit less than this ratio also, or maybe higher than this ratio. So anyone has any doubt up to this?
No, sir.
Okay, all are okay with it? Have you understand why these lengths are A and this length is C by 2 and all? This geometry you have understand it, right? Everyone?
Yes, sir.
Okay. Okay, so next is we have to determine the packing efficiency, right? So what is the packing efficiency? Can anyone unmute and answer? How we define packing efficiency?
So the volume occupied by atoms divided by the total watt molecules.
Yes. So packing efficiency is basically the percentage of the space that are occupied by the atoms. So this can be defined as this ratio, that is the total volume which is occupied by the atoms. So this is basically multiplication of number of atoms per unit cell into volume of one atom. It will be divided by total volume of the unit cell. So we will get that fraction. So packing fraction, if we multiply it with 100, we will get the percentage. So now can anyone tell that what is the total number of atoms in a hexagonal closed packed unit cell? How many number of atoms is there per unit cell? At least you can try. You don't have to give right answer also. This is an interactive session and you all people can think me as a friend also, right? Anyone want to try? How many atoms are there in a hexagonal closed packed unit cell?
12.
How much? 12.
Yes, sir.
How? Why it is 12?
Sir, hexagonal is the top and bottom, the number of six atoms.
Yes.
Total calculate is 12.
Okay, but one more plane is there in between, right? of these two plane. So this is one plane and this is one plane, and one more plane is there in between. So this is the A type plane, this is B type, and this is C type, right? Sorry, this is A type also. So now let us consider first this plane. So in this plane we have 1, 2, 3, 4, 5, 6 atoms there at the corner, one at the face center or base center, right? So these 6 atoms basically contributing to total 6 number of unit cell. So it is this one atom is not contributing only to this unit cell, rather than these atoms are contributing to the other surrounding unit cell also. So one corner atom is basically contributing to the 6 number of unit cell. So what will be the contribution for this unit cell then? 6 into 1 by 6, right? This all these corner atoms. Have you all understood this? And one more atom is at the base center, right? So this base is basically sharing with 2 unit cell, because if we draw the another unit cell at bottom, you can see that this face is basically common with this 2 unit cell. So this one atom is basically contributing only 1/2 to this unit cell and other half to the other unit cell, and this corner atom are contributing 1/6 of to this unit cell, right? So have you all understood this up to this, why this is? Anyone has any doubt can ask. Okay, so for this plane, all these 3 atoms are inside this unit cell only. So all these 3 atoms are basically contributing to this unit cell only. So there is total 3 number of atoms from this plane, and again similarly from this plane 6 into 1 by 6 plus 1 into half. So this is 1.5, this is 1.5, and this is 3. So what is the total number of atoms is there in this unit cell then? 3 plus 1.5 plus 1.5. So total number of atoms for this unit cell is 6, right? Now let's say the radius of one atom is capital R. So what will be the volume of one atom? Volume of one atom will be 4/3 pi into capital R cube. So this is the volume of one atom, and this is the total number of atoms in a hexagonal closed pack unit cell. So now we have to find out the total volume of the HCP unit cell. So how can we find out this total volume of this unit cell? Anyone want to answer? Hello, are you people there? Okay, so how can we calculate the volume then? So we have to first calculate the area of this base of this unit cell and multiply it by the height of this unit cell, that is C, right? So total volume we can write as base area multiplied by height of the unit cell. Height of the unit cell is C, right? So now how can we calculate the base area? So if you see the base of the hexagonal closed bracket structure, it is a regular hexagon, right? So which has 6 atoms at the corner and 1 atom at the base center, right? So if we add this, if we see this plane, you can see that there are total 6 equilateral triangle, right? So the length of this edge is equal to the lattice parameter. So for one equilateral triangle, what will be the area for this equilateral triangle? The area will be √3 by 4 a square, right? So now we have total 6 number of equilateral triangle in the base. So what will be the base area then? 6 into multiply by area of this one triangle. So that is √3 by 4 into a square, right? So now we can write packing efficiency is equal to number of atoms per unit cell, that is 6, into volume of one atom, that is 4/3 pi r cube, divided by total volume. Total volume is base area, this is this one, and height, this is C. So 6 into √3 by 4 a square into C into 100. Okay, so this 6 and 6 will get cancelled out. Now initially we have find out that C by A ratio for a ideal hexagonal closed bracket is 1.633, right? So we can write pi r cube, 4/3 pi r cube, divided by √3 by 4 into a square into C means C by A is 1.633, so C means 1.633 into A, right? Now for a hexagonal closed pack, so this as I told earlier, these atoms are basically touching each other, right? So if the radius of one atom is r, so then this total length, that is A, is equal to 2r, right? So this total length is equal to 2r. So this is the relationship between the lattice parameter and the radius of one atom in a hexagonal closed bracket structure. So now let us substitute this A in the terms of radius of the atom. So we can then write as 4/3 pi r cube divided by √3 by 4 into A means 2r whole square into 1.633 into 2r, right? So now 4/3 pi r cube divided by √3 by 4 into 4 into 1.633 into 2. So there it is r square and here it is r, so it will be r cube. Okay, now this r cube and r cube will get cancelled out, this 4 and 4 will also get cancelled out. So this will be 4 pi by 6 √3 into 1.633. So sorry, there will be 100 is there, as we are writing in the terms of percentage. So anyone have calculator, can calculate this one and check. So this is 4 pi divided by 6 √3 into 1.633. How much it is coming? Have you people calculated? Okay, yes, it is coming 74%, right? So anyone has any doubt till now? Any doubt in this calculation?
No, sir.
All are okay with it, right? Okay. Okay, so we got packing efficiency 74%, right? So the C by A ratio is 1.633 and the packing efficiency is 74%. So the correct answer is option B. Okay, now let's move in the next question. So this is a question from the phase transformation part. So this question is a binary phase diagram is shown in the schematic. So upon complete solidification of a binary alloy system AB, the fraction of proeutectic alpha phase present is 0.5. The alloy composition in terms of weight percent B is. Okay, so it is given that proeutectic alpha phase present is 0.5% or 0.5, that fraction is 0.5. So we need to calculate what is the alloy compositions. So anyone can tell me that what is a proeutectic alpha and what is alpha, what is the difference? Anyone? So there in this question it is asked that what is the alloy compositions in terms of weight percent of B, right? So we can assume that the alloy composition is C naught, right? But we don't know where we should consider the alloy percentage, alloy composition. We should consider in this side or in this side. Anyone? Which side we have to consider? That C naught. Which side it will be there? Okay, left side. Why? Why it should be in the left side? You were right, but do you know why? Yes. So now we have the answer, right? That alpha formed before eutectic points. So this is the proeutectic alpha, right? So when you will cool this alloy composition from this liquid phase, so wait, so this is not the correct location of this alloy composition, right? So when you will cool this alloy compositions, so first the mixture of alpha and liquid mixture in this case above this point everything is liquid. Now when you are cooling this, so after this point alpha will nucleate. So as alpha is nucleating before that eutectic reaction, so it is called proeutectic alpha, right? So this alpha will be there and some fraction of liquid will be there. As you come to this point, so alpha of this composition will be there in your microstructure and liquid of this composition will be there. Now as you cool down below, what phase will form? Alpha and beta, right? Because above this point you have, in this point you have in your microstructure like alpha is there. Sorry, if I write it in the magnified form here, alpha is there and there will be liquid is there, right? Alpha and liquid. Now when you are further cooling down below the eutectic temperature, what will happen? That alpha phase was there earlier, that alpha phase will not change, it will remain there, and that liquid will undergo eutectic reaction, that is liquid will undergo eutectic reaction and it will form alpha plus beta. So this alpha, let's say this, I'm just for the sake of simplicity I'm writing it in a different color. This is alpha. So this alpha, let's say, are formed after eutectic reaction. The compositions will be same only, but as this alpha are forming after eutectic reaction, so this red color alpha or this alpha is means it is not considered as pro-eutectic alpha. So pro-eutectic alpha is the alpha phase that is formed before the eutectic reaction. So this is the pro-eutectic alpha, and that pro-eutectic alpha phase present is 0.5. Not all the alpha phase present. It is not asking about all the alpha phase present. It is only telling that pro-eutectic alpha phase is present, that is 0.5. So now we know that pro-eutectic alpha phase will form up to this part, up to this temperature only, right? When we are cooling up to this temperature only, pro-eutectic alpha will form. It will not form further below this temperature. Below this temperature, the alpha phase will form because of the eutectic reaction only. So upon complete solidification, means we have cooled down to the room temperature here, but as pro-eutectic alpha phase formed at this temperature, up to this temperature only, so we have to consider the tie line at this temperature. Remember, we don't have to consider tie line at room temperature, because pro-eutectic alpha phase formed up to this eutectic temperature only, so we will consider tie line up to this temperature, right? So if we write the tie line here, so this composition is 18.3, this eutectic composition is 61.9, right? Now we assume that the compositions, this is the alloy composition, that is C naught, is in between these two compositions. Now if this length is A, this length is B, now we can apply lever rule, and we can calculate the fraction of alpha phase formed, right? So what will be the fraction of alpha phase that is formed? Can anyone tell me what will be the equation? You all know lever rule, right? Anyone? You can unmute and tell. Yes, you are right. So for lever rule is basically this side is alpha and this side is the eutectic composition, right? So in lever rule we have to take the opposite arm, that is this one. This side is alpha, so we have to take the opposite arm. So this length is B, right? And the total length, that is A plus B, right? So what is the B? B is 61.9 minus C naught divided by total length. Total length is 61.9 minus 18.3. Now this fraction of alpha, sorry, this will be pro-eutectic alpha, pro-eutectic alpha. It is given 0.5. Now we can calculate 61.9 minus C naught is equal to 0.5 into 61.9 minus 18.3. This is 43.6. Okay. So what will be the C naught? C naught is equal to 61.9 minus what will be this one? This one is 21.8. So C naught is how much? 40.1. So what is the composition of this alloy in terms of percentage of B? The composition is alloy actually 40.1 percentage of B. This is 40.1 percentage of B. So this is the alloy composition. So anyone has any doubt why we have taken this tie line, not this one? Everyone understood? Okay, so everyone understood, right?
Yes, sir.
Okay, okay then. Okay, so time is almost getting over, so today I will not start any new question because then it will take time, so I don't want to explain in hurry. So how many people are there? So at least then you people can introduce yourself, like from where you are and from which institute and which year. And if you have any general queries related to the topic covered today, or if you have any query related to the metallurgy, you can ask me. I will try my best to answer those things. Don't hesitate to ask anything. So Devendra Kumar, can you introduce yourself?
Yes, sir.
Yes.
Good evening, sir. Myself, Devendra Kumar. I live in Bhilai in Chhattisgarh.
Okay.
I have an institute in the OP General University in Raigad, Punjipatra. I
Okay.
am third year.
Okay, you are currently in
Thank you.
third year. Okay, okay. Then Subramaniam. Okay. And Sukanna.
Sir, I am from Odisha, from Indira Gandhi Institute of Technology. I'm
Okay.
at final year.
Okay. 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 So, do you people have any doubt or anything regarding any other subject also? You can ask. I will try my best to answer. Anyone? And you also can give us feedback like what you are expecting from this course, how it should be, so that it will help you people. So this is the first week only, so you people can share your feedback also, what you people are expecting from this GATE portal, NPTEL portal. So this idea is basically to help for preparation of this GATE, right? So I will request that if this session will be much more interactive, that will be better for your preparations also. And so the purpose is not only to solve the questions, that this many questions we have solved in this live session. So the purpose is to clear the concepts also, which is linked with the each questions. So any type of doubt if you have, don't hesitate to ask at any point of the time. You can also interrupt in between and ask anytime, right? So everyone is okay, right, with today's session? Okay, what are the reference book that we can refer? Okay, reference book, you can refer like that. One book is there, uh, Raghavan, you know, right? Raghavan and Callister. Both you can refer for crystallography. And for phase transformation study, you can refer that Porter Sterling. This book is very good. Is that phase transformation parts are explained very well in that book. And for crystallography, Raghavan and Callister is enough. Okay. Okay then, we'll meet in the next Friday. I request all of you to attend this live session at every Friday and make this outreach successful. So thank you all. We'll meet in the next Friday.
Thank you, sir.
Thank you. Thank you all.